This is lesson 3 of the final vectors unit. This lesson is on equations of planes. So up until now in this unit we've been looking at different equations of lines, including vector, parametric, and symmetric equations of lines. In this unit we're going to be introduced to planes and learn how to write vector and parametric equations of planes. You could also write a scalar equation of a plane, and that'll be in the next lesson you'll learn that. But in this lesson we're going to be focusing on these two forms of how we write the equation of a plane, and by the end of the lesson you'll understand what all of the components involved in these equations mean, and you'll also be able to create the equations based on given information. So when you're ready, head on over to jensenmath.ca so you can get a copy of the lesson. We're in the Calculus and Vectors course, and like I said, we're in the last unit of vectors, so Unit 3, Lines and Planes, and we're on Lesson 3, Equations of Planes. You can find a blank copy of the lesson here, and you can get practice problems after by clicking here, and you can check your solutions by clicking on Worksheet Solutions after you've tried the practice problem. So when you're ready, let's get started. Alright, before I teach you how to write the equation of a plane, I want to make sure you understand what a plane is. So let's look for a couple definitions of what a plane is. Google Dictionary tells us that a plane,
a flat surface on which a straight line joining any 2 points on it would wholly lie.
Okay, so that's what the Google Dictionary says. It says if we had a flat surface and there were 2 points on that flat surface, if I connected them with a line, that line would lie wholly on that plane. Okay, let's see what a math textbook says. Here's a calculus and vectors text. It says, planes are flat surfaces that extend infinitely far in all directions. Okay, so those are the word definitions of what a plane is. It'll help if you see a diagram. Alright, here in GeoGebra I have it showing you a plane. And notice that plane is a flat surface that extends infinitely in all directions. And also, if we had 2 points on that plane and connected them with a line, that line would lie wholly on that plane. Alright, now that we know what a plane is, what do we need to be able to write the equation of a plane? To be able to write the equation of a plane, we need 3 things. We need 2 non-collinear vectors parallel to the plane. So we need 2 vectors parallel to the plane. They give us the direction of the plane, but those 2 vectors cannot be parallel to each other. They cannot be collinear. And we also need a point on the plane. So we need 2 non-collinear vectors parallel to the plane and a point on the plane. If we have those 3 pieces of information, we can write the vector equation of a plane. Down here, I'm just showing you 4 different things a question could tell you about a plane that would help you come up with the 2 direction vectors and the point on the plane. For example, if I gave you 3 points on a plane, well, okay, so we have a point on the plane, and we could find direction vectors by finding vectors that connect those points to each other. So I could find vector AB and AC. Those are vectors parallel to the plane that are not parallel with each other. So those would be fine for direction vectors. And if we look at scenario A, if I gave you a line on the plane and a point on the plane, well, okay, we have a point on the plane, and the line has a direction, so that's one direction vector. If we wanted another non-collinear direction vector, I could just find any point on the line and find the vector that connects that point to this known point, and that gives me a second direction vector. So I won't go through all 4 of the scenarios, but I'm just showing you these are some scenarios where we could come up with 2 non-collinear vectors parallel to the plane and a point on the plane. Okay, now you might be thinking, well, why do we need 2 direction vectors and a point on the plane to be able to define a plane? Let me give you a visual demonstration. Well, when we were working with defining lines with a vector equation, you learned that in order to define a line with a vector equation, we had to come up with a resultant vector that could point to any point on the line. And that resultant was a sum of a position vector, a vector that pointed to a point on the line, and a scalar multiple of a direction vector, a vector parallel to the line. If we added those 2 vectors, we got a resultant vector that could point to any point on this line by varying that scalar multiple of the direction vector. Okay, so why for a plane do we need a position vector and 2 direction vectors? Well, here's that plane I was showing you. If I wanted to be able to define this with a vector equation, I need to come up with a resultant vector that could point to any point on this plane. So first of all, we need to know a point on the plane so that we could come up with a position vector that has its tip at that point on the plane. So we start with that position vector, that has its tip at a point on the plane. And then to that position vector, I need to add two non-collinear direction vectors that are parallel to the plane. So here's my first direction vector. Notice that that direction vector lays on the plane. That's what makes it parallel to the plane. And now I also need another direction vector that is parallel to the plane, but not parallel to that first direction vector. So here it is here. If I were to add these three vectors together, this position vector with these two direction vectors, the resultant would have its tip at a point on the plane. So how can I point to any point on this plane? Just multiply those direction vectors by a scalar multiple, and that would allow me to get my resultant to go to any point on the plane. And let me show you that. So watch the tip of the resultant vector. Notice how it's going to points on the plane. So I'm varying the scalar multiple of my first direction vector A, and then also I could vary the scalar multiple of my second direction vector B to allow me to get to other points on the plane. And by varying those two scalar multiples of the direction vectors, I could be able to get to any point on this plane that I want to. So that resultant vector, the resultant of the position vector and the two scalar multiples of the direction vectors, allow me to have the resultant vector pointing to any point on the plane, so that resultant vector defines the plane. So in this lesson, we're going to be focusing mainly on the vector equation of a plane. We'll also talk about the parametric equation, and scalar equation of a plane is next lesson, so stay tuned for that if you're interested in the scalar equation of a plane. But like I just said, the vector equation of a plane is a sum of three vectors: your position vector plus scalar multiples of your two direction vectors. And when working with planes, we're always working in 3 space. So our resultant vector is going to be vector x, y, z. It's going to have an x, a y, and a z component. And our position vector and two direction vectors also have 3 components each, because we are always working in 3 space when we're working with planes. So if you take a minute just to read this section, it just outlines what I've already told you about what each of these components mean in this vector equation of a plane. If we know the vector equation of a plane, the natural next step, which is very easy to do, is to break it into its parametric equations. That's just an equation for the x, the y, and the z component. So if we have the vector equation of a plane here, when I calculate the resultant vector, I have to calculate the x component by doing the x component of the position vector plus the scalar multiple of the x component of direction vector 1 plus the x component of the scalar multiple of direction vector 2. That's where this equation comes from. X naught plus t times a1 plus s times b1. And same rationale for getting the y and z equations. Let's actually get started with an example now. So let's consider the plane with direction vectors a equals 8, negative 5, 4, and b equals 1, negative 3, negative 2 through this point. So we know a point on the plane and we know two direction vectors that are parallel to the plane. And those direction vectors are not collinear, I can tell, because they're not scalar multiples of each other. So let's start by writing the vector equation of the plane. So x, y, z equals a position vector is a vector that starts at the origin and has its tip at a point on the plane. So it needs to have its tip at the point 3, 7, 0. So I'll write that as the vector 3, 7, 0. And to that position vector, I then need to add scalar multiples of both direction vectors. So plus t, that's just some scalar of direction vector a, which is 8, negative 5, 4, plus another scalar multiple, so choose a different variable, I'll choose s for that scalar, times direction vector b, so 1, negative 3, negative 2. So this resultant vector defines the plane that I've been showing you so far. So this is the vector equation of a plane. It has this position vector plus a scalar multiple of that direction vector plus a scalar multiple of that direction vector. When I add those 3 vectors together, the resultant vector will always point to a point on the plane. No matter what I make the scalar for direction vector 1 or direction vector 2, notice the resultant vector will always be at a point on the plane. So no matter how I vary those scalars, that resultant vector always has its tip at a point on the plane. Okay, let's write the parametric equation of the plane. When writing the parametric equation of lines, we wrote L and then the parametric equations. But for a plane, we'll use a Greek letter P. That's the pi symbol. And now we'll need the 3 parametric equations. One for the x component. The x component will be calculated by doing 3 plus t times 8 plus s times 1. So 3 plus 8t plus 1s. The y component would be calculated by doing 7 minus 5t minus 3s. And lastly, the z component would be calculated by doing 0 plus 4t minus 2s. So now we have both equations, the vector equation and the parametric equation of the plane. Alright, part B is a continuation of the plane we were working with in part A. We're just checking to see if this point is on that plane. So to check if that point's on the plane, we're going to need that plane's parametric equations. Let me copy and paste those over. Alright, so there are the parametric equations. We have an equation for x, y, and z. If this point is on that plane, I should be able to find a single set of t and s values that get me to that x, y, and z coordinate. So when I plug the x, y, and z coordinates into their respective equations here, I should get a single set of t and s values that work for all three equations. So let's start by setting up our three equations. To make equation 1, I'll set x equal to the x coordinate. My second equation, I'll set y equal to the y coordinate. And for my third equation, I'll set z equal to negative 6. Negative 6 equals 4t minus 2s. That's my third equation. Now I'm looking to try and find a single set of t and s values that make all three of these equations true. I could find a single set of t and s values that make any pair of these three true. And that's what we're going to do to start off with. I'll pick any pair of these, so either equation 1 and 2, 1 and 3, or 2 and 3, and solve for t and s that make those two equations true. And I can always find that. But then the important part of this question will be then checking if those solutions for t and s also make the third equation true. If they do, that means the point is on the plane. If they don't, that means the point is not on the plane. So the pair of equations I'm going to choose to use are equation 1 and 2. Like I said, you could do any pair, but I'll choose equation 1 and 2. And now with equation 1 and 2, I'll solve for both t and s that make those two equations true. And I'll do that using elimination. So I'll choose to eliminate the s variable. So I'll need the coefficient of the s in equation 1 to be either 3 or negative 3. I'll make it 3. So I'll need to multiply equation 1 by 3. And I'll get negative 30 equals 9 plus 24t plus 3s. And I'll leave equation 2 exactly as it is. And if I add these two equations, the s's will eliminate. That's why this is called elimination. So add all the like terms. Negative 30 plus 8, that gives me negative 22. 9 plus 7, that's 16. 24t plus negative 5t, that's 19t. 3s plus negative 3s is 0s. So they eliminate. Now let's solve for t in this new equation that we made here. Subtract the 16 over, I get negative 38 equals 19t. Divide both sides by 19, I figure out t equals negative 2. Now what we have to do is solve for s by subbing t equals negative 2 into either equation 1 or 2. Not into 3, it has to be 1 or 2, because those are the two equations we used to solve for t equals negative 2. So let me make a note of what we're doing now. So we will get the same answer for s, no matter whether we sub t equals negative 2 into equation 1 or 2. But I'm going to choose equation 1. So negative 10 equals 3 plus 8 times t, and we solve t to be negative 2, plus s. And now let's solve this equation for s. So I'll subtract the 3 over, negative 13 equals negative 16 plus s. Add the 16 over, I get s equals 3. So I've now solved for s and t that make equation 1 and 2 both true. So that'll get me to the correct x and y coordinate. But do those t and s values get me to the correct z coordinate? So we have to check the t and s values into equation 3. This is the important part of the question. Test if t equals negative 2 and s equals 3 satisfy the third equation. So I'll separate the third equation into left side, right side, and see if those t and s values make the equation true. So the left side was just negative 6, and the right side was 4t minus 2s. So let's sub in negative 2 for t and 3 for s. Negative 8 minus 6, that gives me negative 14. So notice the left side and right side are not equal. That tells me that the point is not on the plane. There's not a single set of t and s values that make all three equations true. So since left side does not equal right side, I could say point Q is not on the plane. Let me just show you in GeoGebra what we just did. I have that point Q plotted. Notice that point Q is over here. It's clearly not on the plane. Let me just spin it so you can see point Q not on the plane. I have the equation of the plane written as the vector equation, the sum of the position vector and the two direction vectors. And we figured out that if we were to set the t parameter to negative 2, let me set it to negative 2, and the s parameter to 3, which I already have it set to 3, it would take me to a point that has the correct x and y coordinate, but not the correct z coordinate. Right here I have the resultant vector showing me the x, y, and z components. It takes me to an x coordinate of negative 10 and a y coordinate of 8, but it does not take me to the z coordinate of negative 6 that point Q has. It takes me to the z coordinate of negative 14. When we did our left side, right side check in equation 3, we got negative 6 does not equal negative 14, right? We figured out it takes me to negative 14, but we wanted it to take me to negative 6. Part C says find the coordinates of two other points on the plane. So basically we can just pick any scalar values we want for t and s as long as they're real values. So let me start by copy and pasting the parametric equations over. I think that's the easiest to work with. And let's find 2 points. Point 1, we can choose anything we want for t, so how about 1? And anything we want for s, how about 2? And now let's calculate the value for x, y, and z with those two scalar values chosen. X would equal 3 plus 8 times 1 plus 2. That would be 13. Y would equal 7 minus 5 times 1 minus 3 times 2. 7 minus 5 is 2, minus 6 is negative 4. And z would equal 4 times t, so 4 times 1, minus 2 times s, so 2 times 2. So 4 minus 4 is 0. So since we know the resultant vector has its tip at a point on the plane, we could say that the point 13, negative 4, 0 is on the plane. Let's just verify that in GeoGebra. So let me just change this point down here, point Q that wasn't on the plane. Let's change this to 13, negative 4, 0, and let's see if that's on the plane. Yes, that point right there, clearly on the plane. So we found one point that's on the plane. Let's find another point that's on the plane. Shouldn't matter what I choose for t and s. Any scalar multiple of those direction vectors added with the position vector will give me a resultant that points to a point on the plane. So point 2, let's choose t equals 0 and s equals 2. So x equals 3 plus 8 times 0 plus 2. That'll give me 5. And y would equal 7 minus 5 times 0 minus 3 times 2. So 7 minus 6, that's 1. And z is just 4 times 0 minus 2 times s, which we chose to be 2. This gives me negative 4. So the point 5, 1, negative 4 should also be on the plane. Let's double check to make sure it is. 5, 1, negative 4. There it is. It's right there, point Q, on the plane. And what we did was we chose the scalar multiple for t to be 0. Let me move it to 0. And we chose the scalar multiple for s to be 2. And it gave me the resultant pointing right to that point that we found. 0.51, negative 4. Right? It wouldn't matter what we chose the scalars to be for t and s. It would always have a resultant that points to a point on the plane. So that's why we could have chosen any values we wanted for t and s. D says find the x-intercept of the plane. Well, what do I know about an x-intercept? An x-intercept has a y and a z component of 0. So here are the parametric equations of that plane again. I know the x-intercept has a y and a z of 0. So what I'm going to do is I'm going to set y and z to 0. And then with these two equations, solve for what value of t and s, make those equations true, and then sub those values for t and s back into this here, and then solve for x. So I can solve for t and s in these two equations using elimination again. So I think I will choose to eliminate the s variables. So I will multiply the top equation, equation 1, by 2. And I'll get 0 equals 14 minus 10t minus 6s. And I'll multiply the bottom equation by 3. 0 equals 12t minus 6s. And then if I subtract the like terms in these equations, the s variable will eliminate. 0 minus 0 is 0. 14 minus nothing is 14. Negative 10t minus 12t is negative 22t. Negative 6s minus negative 6s is 0s. And now I'll solve this equation for t. 22t equals 14. T equals 14 over 22, which reduces to 7 over 11. So that's the value for t. Sub that back into equation 1 or 2 to solve for s. So I will sub t equals 7 over 11 into either of them, into 1 or 2. I'll sub it into 2 because that'll be easier to evaluate, I think. But I'll get the same answer either way. So 0 equals 4 times 7 over 11 minus 2s. 0 equals 28 over 11 minus 2s. 2s equals 28 over 11. Divide the 2 over, and I get s equals 14 over 11. So I have the values for s and t that get me a y and a z component of 0. So I know it's going to bring me to an x-intercept. But what is that x-intercept? What is the x-coordinate when s is 14 over 11 and when t is 7 over 11? To find that out, sub t equals 7 over 11 and s equals 14 over 11 into x equals 3 plus 8t plus s. So I have x equals 3 plus 8 times 7 over 11 plus 14 over 11. So I'm going to need a common denominator, so I'll rewrite that 3 as a 33 over 11 plus 56 over 11 plus 14 over 11. If I add these 3, I get 103 over 11. So the x-intercept is 103 over 11, 0, 0. And I figured that out by figuring out that value for s and that value for t, make the y and z components both be 0, and they make the x component be 103 over 11. Let's verify that in GeoGebra. So we figured out a t value of 7 over 11 and an s value of 14 over 11. Take me to the x-intercept, right? Yes, the resultant is now pointing to a point on the x-axis. And what are the coordinates of that point? Well, I have the resultant right here, 9.3600. Let me just show you that 9.36 is the approximate value of 103 over 11. By plotting the point 103 over 11, 0, 0. Notice, yes, that point is the point we found. It is on the x-axis, so it's an x-intercept. That point has an x-coordinate of 103 over 11, a y-coordinate of 0, a z-coordinate of 0. For example 2, we should be able to do this a bit quicker now that we know how this all works. Example 2 says find the vector and parametric equations of each plane. So part A, we're given 3 points on the plane: the x-intercept, the y-intercept, the z-intercept. So the x-intercept is 2, so that means the point 2, 0, 0 is on the plane. The y-intercept is 4, that means the point 0, 4, 0 is on the plane. And the z-intercept is 5, that means the point 0, 0, 5 is on the plane. Let me just show you in GeoGebra what we have and what we need to be able to write the vector equation of this plane. So we have these 3 points on the plane, the x, y, and z intercept. So let me show you, there is only one plane that contains all three of those points. There's the plane there. We need the vector equation of this plane. So for the vector equation of this plane, we need to find a resultant vector that can point to any point on this plane. And the resultant vector is going to be the sum of three vectors. It's going to be the sum of a position vector, a vector that points to a point on the plane, and then two non-parallel direction vectors. So those direction vectors I could create by finding the vector that connects any two pairs of these points. So either xz or zx, or xy or yx, or vector yz or zy. And once I find those two direction vectors, I can add scalar multiples of those two direction vectors to the position vector, and then I'll get a resultant vector which will always have its tip at a point on the plane, no matter how I vary the scalar multiples of those direction vectors. Notice as I vary the scalar multiples of those direction vectors, the tip of the resultant vector is always going to be at a point on the plane. That's why we call it the vector equation of the plane. So we have to come up with the position vector. So a position vector is a vector that points to any point on the plane, and we usually call that position vector vector r0. So I'll make it point to the x-intercept. So the position vector would be the vector 2, 0, 0. And then I need two direction vectors. Direction vector 1, I'll make it the vector that connects point x to point y. So vector xy can be my first direction vector. And when I find vector xy, I would have to do always tip minus tail. So to get the x component of the vector, do the x coordinate of the tip minus the x coordinate of the tail. 0 minus 2 is negative 2. To get the y component of the vector, do y coordinate tip minus y coordinate tail. 4 minus 0 is 4. And to get the z component of the vector, do the z coordinate of the tip minus z coordinate of the tail. 0 minus 0 is 0. And now to get my second direction vector, I do the same thing, but to connect a different pair of points. I can't do vector yx now because that would be collinear with xy. I need a non-collinear direction vector. I need another direction vector that is not collinear with the first one. So I could do xz, zx, yz, or zy. I just can't do yx. So let's do yz. 0 minus 0 is 0. 0 minus 4 is negative 4. And 5 minus 0 is 5. So the vector equation of the plane would be xyz equals 2, 0, 0, that position vector, plus scalar multiples of the direction vectors. So I'll say t times direction vector 1, so t times vector negative 2, 4, 0, plus a scalar multiple, I'll make that scalar multiple s, of direction vector 2, 0, negative 4, 5. So that's the vector equation of the plane. Let's also write the parametric equations. So we'll write pi, Greek letter p, standing for plane, and then I'll write my x, y, and z equations for how we get those components of the resultant vector that defines the plane. So x would equal 2 minus 2t plus 0s, y would equal 0 plus 4t minus 4s, and z would equal 0 plus 0t plus 5s. So we have both the vector and parametric equations of that plane. Part B says the plane containing the line xyz equals 0, 3, negative 5 plus t, 6, negative 2, negative 1, and it's parallel to this line xyz equals 1, 7, negative 4 plus s, 1, negative 3, 3. Notice equations of lines look very similar to equations of planes, but we only add one direction vector to the position vector. That's how we know it's a line, not a plane. So we know it contains this line. So that would mean that the position vector 0, 3, negative 5, we know that has its tip at the point 0, 3, negative 5. We know that point will be on the plane if the line itself is on the plane. So we know a point on the plane. Point 0, 3, negative 5. That means a position vector we could use for the plane would be equal to the position vector 0, 3, negative 5. I can use the same position vector that was used for the line that's on the plane. And since I know that the line is on the plane, I know that the direction vector used for that line would be parallel to the plane as well. So a direction vector for the plane would be 6, -2, -1. Now let's look at what the second line tells us. We know that it's parallel to the second line. This second line has a position vector that has its tip at a point on the line, but I don't know if the line is on the plane. I just know it's parallel to the plane, so I can't use the position vector. But I can use the direction vector as long as it's not a scalar multiple of the direction vector I've already used. And it's not. They're clearly not scalar multiples of each other. So since I know line 2 is parallel to the plane, I know its direction vector is parallel to the plane, so I can use that direction vector. So direction vector 2 is 1, -3, 3. And that's all the information I need to write the vector equation of the plane. The vector equation of the plane would be x, y, z equals the position vector, 0, 3, -5, plus scalar multiples of both of the direction vectors. So plus t times the first direction vector, plus s times the second direction vector. That would be the vector equation of the plane. To write the parametric equation of the plane, we just break it into its x, y, and z equations. So to get the x component of the resultant vector that would have its tip at a point on the plane, I would do 0 plus 6t plus 1s. Y would equal 3 minus 2t minus 3s. And z would equal -5 minus 1t plus 3s. So those are the parametric equations of that plane. So these are just two different ways of describing the same plane. Okay, so that's it for the lesson, but there's tons of ways I could give you information that would be enough to be able to write the equation of a plane. So make sure you actually go through and try the practice problems so that you can see all the different variations of how I could ask you these questions.